Hello, this is Jenna Zahid, and today I'll be discussing my lab, motion in a single direction. So, the purpose of this lab is to observe the motion of an object in a single direction as it moves towards the right, and we discuss its displacement, velocity, and acceleration. We notice it in the stationary lab. The physical concepts we have explored include momentum, change in momentum, which is impulse, push and pull forces, and Newton's first and second laws of motion. And through this lab, we can notice that the force applied to the object did change its position. It applied the positive net momentum to the object as it moved, but then we see that the forces seem to stabilize as the push and pull forces begin to be equal, and then the object moves with constant velocity. So for the physical ideas, momentum is a product of velocity times mass, it's mv, and its change is just impulse. So at the start, it was given an impulse towards the positive direction, so it can prompt the cart to move because it was stationary. It gave it an initial velocity of 0.1 meters per second, and the interval of motion was about 2.6 seconds long. There was some friction from the track. That was one of the main physical ideas we have noticed. It was either from the friction from the track or the air resistance, and there was a net change in momentum, but then the object was moving with a constant velocity by the end of the motion. So here are the graphs we have acquired. We can see a positive change in the x direction, in the x axis, and we can see a positive change. We can also see a change in velocity and acceleration, but when we take the average of acceleration, we can see that it reaches zero by the second half of the journey after the net forces are stabilized. For the system of the experiment, it includes the cart, the track, and the potential frictional forces. The surrounding includes the push force in the beginning of the journey, the air resistance, and the gravitational forces exerted by the Earth. For the initial conditions of the experiment, the object was completely stationary, but then after the force that was given, it had 0.1 initial velocity and a positive acceleration of about 1 meters per second squared, but then it reached zero. For the experiment, first we check that the track is level. We place the cart on the origin. We push the cart towards the right side. We recorded the video and we tracked the displacement, velocity, and acceleration. And we tracked the patterns and concluded results. For the equipment, we used the cart, track, phone, and the NASA software. So here's an example of the tracking software we have used. We have manually tracked the position of the object as it moved. Um, for the possible sources of errors, there was unstable videotaping because the phone was not placed on a stationary object. The track was not level. In the beginning, we tried our best to make it level, but we didn't have a professional tool to make sure it's level. And the tracker manual tracking is not the best because it's produced by humans, and humans are prone to error. So for the results, there's a constant movement towards the positive x direction. After the push force was applied, there is a fluctuating velocity and acceleration, but when we take the average of them, we notice that the net force seems to be zero, and the velocity and acceleration increased when the force was applied, but reached a higher value from its initial condition because the object was completely stationary, but then it was moving with that velocity as a constant velocity throughout the rest of the journey. For the conclusions, the velocity and acceleration both increased due to the push force because there was an applied change in momentum. It was an impulse. There's fluctuations in velocity and acceleration, most likely because of the friction that was not part of the system. We noticed pull and push forces that balanced out by the end, and any applied force prompts a change in momentum. This was a generalization we made after noticing the details of the experiment. For the coding details, we have edited the script. So the first thing was we edited the initial position and velocity vectors so it can match up with the given graph. We edited the while loop in order to make it 5 seconds, which was the time frame we were looking for. We also changed the initial position because it was different. We wanted to use the momentum principle, and we had to change. Also, we created an extra if statement in order to account for the motion change after 2 seconds because there was a change in velocity. And also, we added a factor of 0.03 negative in order to ensure that the scaling of the graph was correct. For the model prediction versus data, so the model prediction matches the data acquired from the experiment. It predicts a constant velocity motion by the end of the motion, and that was correct. That was a similarity. And the forces do stabilize. That was also another similarity. However, some of the differences that we noticed was that the model didn't accurately display the change in force initially after we pushed it with our hands. Also, the card seems to start off with no positive acceleration in the beginning, but we know that that's true because there was an imbalance in the net force in the beginning, but then the force is balanced out as the card starts moving. So the results would change if it was in the x, the y direction because the forces are different. We would have gravitational force and normal force instead of the applied force and frictional forces, and therefore we would not notice any trends because the card is not moving up and down. It's just moving to the right. Also, we can check for the amount of force that was applied or the push and pull to some extent of accuracy. We can use the momentum principle, the impulse momentum theorem, which is mv equals f delta t to calculate it from the graph.